Hello, Mr. Ryan, right?
Yeah.
Okay, so let's say we are given a binary tree. What's the binary tree?
It's a tree with numbers.
It doesn't have to be necessary numbers. Sometimes you can put the strings, the objects,
Biscuits.
biscuit objects, the sets, anything. Basically, trees, data structures, is used to store the data, right? So what's data structure? The kind of the thing for computer to store the data, to store the data. So this is the binary tree, and we have a copy of it. Let's say we have a clone, copy, exactly the same tree. It's a clone, so it's a duplicate. Look, these two trees exactly, but they are not. Their identity is not the same. They just the value is the same. If we are given a node here, for example, if we are given this node, number 5, okay, you are given these two trees A and B, right? So if we are given if we're given this target node equals, let's say, 5, we need to find the corresponding node in the copy tree, which is this 5. Okay. So if we given this 5, we need to return this 5. If we given this 2, we need to find it in the copy one. Okay. So clone. What's clone? What's the clone?
Clone is a copy.
Copy. Where down?
A, B.
Okay. So
A equals B.
yeah. Okay. So in the equal sign, remember A equal. In Python, we use double equal, right? This is to check the values. For example, A equals 1, 2, 3. This is the list. B equals 1, 2, 3. If we say A equal B, we check the values. So
that means if it's A equals B.
So it should return true because look, these two, the values are the same. That will return true. But another one, A is B. So can you guess? Should it return true or false?
False.
Yeah, we're done. Exactly false. Is means the identity, right? So if the value is the same, if they are different copies, for example, in memory, in computer RAM, look, this A and B, actually they are located as separate memory. So A is here, 1, 2, 3. B is here, 1, 2, 3. So even the contents is the same, but they are different. Okay?
Yeah.
So the is identity. So basically this is the same thing as ID. There's an ID function, ID A equal ID B. Okay? So ID of parameter, this parameter for the ID, it returns a memory location. It's a number. If we print the ID A and B, there will be two different numbers, which means they are different. Right? They are different. It checks the identity. But if this one, look, if I say B equal A, then A is B, that will return true.
Yeah.
Got it? Right? Because B is an alias.
Yeah.
So the shallow copy is an alias. Right? It's not actually an individual copy. Okay? Make sense? Okay, so here, look, A and B. B is a separate. Okay? It's a separate tree. But if we are given a node, in the tree A, we need to find the corresponding one in the tree B. Because these two trees share the same structure.
Yeah.
The structures, the numbers and the values for each node. Okay. So, what's your thought? How can we solve this problem? I mean, first of all,
we can solve it by depth of search, breadth of search.
exactly. Yeah. Given the binary tree,
Yay!
given a graph, two most popular tree traverser or graph traverser is depth search or breadth search. Okay. And for depth search, we can implement using the recursion or iterative. And for breadth search, we travel the tree level by level, and we're using the DQ. For the depth search, we use the stack. If we implement using the recursion, the computer maintain the stack for us, but we can implement it using iterative. And in this case, we have to, maintain a stack ourselves. Okay. So, what's the difference between depth search and breadth search?
Depth of search uses stack and breadth of search uses cube.
Apart from this, what's the difference? What's the major difference of the depth search and breadth search? I mean the
Different names.
the how we traverse the tree. I mean, in terms of the order we traverse the tree. Anybody agree?
Research line by line.
Yeah, level by level. And depth search. On the other hand, then what's the depth search doing? For example, the depth search for this one, for the tree, what do we get? If we're using the pre-order, let's say node, left to right. Okay, so what's the pre-order, depth search pre-order of this binary tree?
1, 2, 4, 5, 3, 6, 7.
Exactly, okay? And the breadth search is 1, 2, 3, 4, 5, 6, 7, exactly. Okay, let's implement the depth search today, okay? It should be quick and easy. Yeah, we have seen this depth search many times. Depth search, breadth search are the most important thing. I mean, I want you to understand during these more than 400 days, yeah, of teaching. That's the most important takeaway because depth search and breadth search are the two most popular, important, very useful tree, graph, traversal algorithm. And it can be used to solve many problems, right? As we can see, we use the depth search, breadth search to solve lots of the tree, graph problems, right? Another thing to notice is the depth search. Look, if this is the depth search, if we want to find the solution, tree traversal, yeah, if we want to locate a node, yeah, sometimes the depth search are quicker to find the solution, right? For example, if the solution is here, yeah, okay, if the solution is here, which algorithm do you think it's better to find the solution quicker? Depth search or breadth search? If the target node is here, we are trying to find exactly because look, it finds it, right? And how about if a node is here, which method? Breadth search. Yeah, you see? Yeah, you see? So it depends on the problem. Yeah, depends on problem. Breadth search. If we find it, if we're doing the breadth search, we find it, it's the shortest path. If the edges are unweighted, the cost of between the nodes is unweighted, right? Do you remember the graph? Yeah. Sometimes the graph has this weight. Yeah. That's 1. The cost of going from A to B is 1. The cost of going from A to C is 3. These are the weights. Yeah. If we are using the breadth search on an unweighted graph, right? Then you will always find the shortest path, right? Shortest path, because it travels level by level, and whenever we found it, and it will be the shortest to the root, right? But for the depth search, not necessary because for the depth search, it may not be guaranteed to find an ultimate solution. For example, look here, you may find this first, right? But sometimes the ultimate solution is here, right? If this is also okay, but it finds this node first, then this is not optimal, right? Do you get it? Yeah. If these two nodes are both okay, if using the depth search, you find this node is not optimal. But for the breadth search, it's always guarantee us to find an optimal solution. In this case, optimal means the shortest path, okay? But we also talk about the iterative deepening, right? Iterative deepening search. Long time ago. First of all, we set the maximum depth to 1. Then we do the depth search. If we can't find it, we set the depth. We increment the max depth to 2, and then we use the repeat this depth search. If we can't find it, we increment the path, right? Increment the maximum limit. Okay, and for the depth search, we don't need to store all the nodes of the same level. But for the breadth search, we need to use the queue to store all the nodes in the same level, right? That's the one disadvantage of using the breadth search, is that it may be memory inefficient. Yeah, make sense?
Yeah.
Okay. That's a lot of things to digest, right? Let's using the depth search. It should be very easy. The recursion easy. Define depth search. We want to find that this is the original tree, this is the clone tree, and this is the target, right? If not A, then we return. Yeah, we can't find it. We return. If A is T, okay, because T is a node in the tree A, so then we can use this identity check, right? Then we can set it to set the answer equals B, and then we return. And then we can depth search A dot left, B dot left, T. And then we also need to search the right tree. Yeah? Therefore search A dot right, B dot right, T. Okay? We are given this node T, which is a node in A. We want to find the corresponding node in B. Right? So we just do this depth search. You see? The order of traversal, the left and right tree does not matter. Right? This is all the depth search. When we found it, when A is T, or you can say A equal T. That's not identity check, that's the value check. Okay, so it's better to do this is because T is given a node in A, right? If the tree contains the duplicate number, then if we put it A equal T, which might not work, right? Because it might return incorrect node. Okay, this is one way. Another way, if we want to return this, return a node for the depth search, we can do this. A, B, T, okay? If not A, return nothing, alright? Return none, okay? Or return nothing, or we just return. By default, it's return none. If A is T, then we return, instead of setting self to answer, which is the outside the scope of the function, then we return B. If A is T, then return B. Then we need to go in the left tree, right? So X equals depth search A dot left, B dot left, T. Then if we found it, yeah? If we found it, then we return X, yeah? Otherwise, we return. If it's not in the left tree, then let's try it at the right tree, okay? B dot right. What's these two implementation in common?
They're similar.
They're similar. Yeah, obviously they're similar. What's the common thing? Can you find the common bit? What are these two in common?
They both have a ABT.
That's more like syntax. I mean, what I mean is algorithm.
If that.
Depth search. Okay, they both depth search and they both implemented in.
Stack.
Yeah, what's the algorithm?
Recursion.
Recursion. Yeah, they're both recursion. Yeah. Okay, and they both traverse the left tree first and then the right tree, right? And then look this one. If we found a node in the left tree, we return without searching the right tree. This one is the same. If we found it, we set the self to answer equals the corresponding node in the clone tree, and we return without keep going, right? Okay. The time complexity (on) if there are n nodes in the tree, in the binary tree. The space complexity (on), yeah, because we are using the recursion, and in the recursion, the computer needs to maintain the stack for us. Yeah, there will be a calling stack, right? Every time the computer makes a call, do the function call, it needs to push the parameters into the stack. Okay. Okay. One last question. What have you learned today?
About finding a corresponding node of the binary tree in a clone of that tree.
Okay, so we are given a node in the tree A, and tree B is a clone, is a copy of the tree A. So basically there are two trees, they are separate two trees, but these two trees look exactly the same. The structures and the values exactly the same. And we are given a node in the tree A. The task is to find the corresponding node in the copy, in the clone tree. Okay. The algorithm we are using is depth search. The depth search, we can use the recursion, which we talked today. And tomorrow we're going to use the iterative approach to implement the depth search. And the day after tomorrow, we're going to use the breadth search. Okay? Yeah, that will be it for today. Bye bye.